Good morning, everybody. It's a high-tech presentation today, so I had to get everything straightened out. You saw my involvement was to get over here out of the way and let somebody who knew what they were doing take care of it. Let's start our meeting with a word of prayer. Heavenly Father, thank you for this beautiful day you have made. Thank you for the opportunity this brotherhood known as the Trinity Men's Breakfast Group has to learn about our vast universe and the place of Earth in that universe. Watch over our friends and family and loved ones. Bring them happiness, keep them healthy, and keep them safe. And Heavenly Father, use us to serve your purposes in this world, to follow the example of selflessness set by your Son, Jesus Christ. In Christ's name we pray. Amen. Any announcements? John?
Our speaker next week will be our own Richard Griffiths and Frank First. They're going to talk about a bike trip they made this summer, 800 and some odd miles down the Rhone River, I believe, and they're going to be here to tell us about it.
Tom?
I'm making this presentation on behalf of John Shepherd and myself. When Anita and I moved to Canterbury, I gave away my bracing bits. And then we got to working on the trail some and we needed one. I found one in a kind of garage sale. And the kit, or the way that the bits were housed was just about to fall apart. And Peggy made us a new thing for it. And when I was moving the bits from the old one to the new one, I found a bit that I didn't even know was there. And it's a 5/32 bit for a bracing bit. And I thought y'all might like to see that. If you think using a sledgehammer to drive a tack or something, I think this is kind of you'll love picking work on this. Waiting on you.
Thank you for that lesson. We're all, yeah, all right.
We have a wonderful resource downstairs at Trinity School for new members. And whenever a young father is taking a child, I speak to them and tell them about the breakfast. And this morning it worked. Drew, tell us.
Hi, this gentleman asked me to join this breakfast group this morning. My children have been members and students at Trinity for the last 5.5 years. And so I appreciate the invitation. I never, fail to take you up on it. So I appreciate you letting me intrude and join in this meeting, and excited to hear about the universe. I'm Drew Lewis, by the way. I live just down the street in Spring Lake, and we're here basically 5 days a week. So nice to meet some of you all.
Great to have you here. Tim, if I leave anything out, one of the things I enjoy about having speakers from our group is that we learn a lot about these people. And I've known Tim, we both joined the church about the same time back in the mid 70s. And, but I didn't know a lot of these things about Tim. Tim attended the University of Tennessee, Martin. He graduated in 1960. Before that, he was the trombonist in a dance band in high school back in the 50s when they had the big bands. He then attended, what's that school that beat Alabama in football? Vanderbilt. He went to Vanderbilt Law School, and he graduated. He was on the Order of the Coif and Law Review. So he was a good student. He, while he was in law school, he operated an FM country music radio station and was the director of music at that station in Blue Ridge, Georgia. know how he attended law school one place. We won't ask about that, but he did well. So somehow he's a smart guy. He also got his Master of Laws degree in Bankruptcy and Uniform Commercial Code at Emory Law School. And I believe that was 72 when you finished up that degree. He practiced in the area of bankruptcy initially and then banking law later in his career. He likes education, so he went back to Georgia State University, and in 2009, he got an undergraduate degree in creative writing, and he used that during COVID, sort of. Maybe it was a little bit before COVID. In 2021, he had his book published, a book called Riley and Ben. He has had 6 children and 13 grandchildren over time, and probably leaving something out here, but the most important thing, he's married. Oh yeah, he's broke. Anybody who wants to contribute, he has 5 grandkids in college. He's apparently footing the bill for all these. Tim? Green light, Tim. That's good. Hey, welcome, Tim.
Well, thank you. I don't know where the information got off track about the radio station. It wasn't while I was in school. It was after I was practicing law in Atlanta. And with the telephone and the budding internet, running a radio station from Atlanta is not a difficult job. So that got done. Am I speaking loud enough?
Yeah, you're fine.
How about that? Better? I want to tell you that Ruth woke me up when she read the email from Trinity this morning, gave me my coffee in my favorite cup, and told me I could go back to bed. I'd been preempted by Monty Python. So I don't know how many of you watched the Monty Python blurb this morning, but I'll tell you it is dated. Things have happened since 1983. Excuse me, I need my glasses. And I'll also tell you that I'm not a scholar, I'm a lawyer. But I do have an intense interest in astronomy and cosmology, which started when I was in a small town in West Tennessee, looking up at the beautiful sky at night and counting all the stars. And then when I was 11, I went to Hayden Planetarium and got a professional look at things, which was eye-opening for me. I want to say that a lot has changed in the last 73 years since I was at the Hayden Planetarium. First, we now know pretty much the age of the universe, subject to a caveat. We also know pretty much how big it is, again, subject to a caveat. So there are a couple of bits of information that I've brought together for you today. We're going to play these 2 videos, which will let you know a little bit about how big the universe is, and then we'll have a little talk after that. Okay, so here we go, hopefully.
Earth, our home planet, a tiny blue dot floating in the immense cosmic ocean. Here resides everyone you ever knew, every human who ever lived, every story that was ever told. It's where our journey begins, but as we zoom out, beyond our atmosphere, past the moon, beyond the familiar planets and the sun, we embark on an epic quest, a quest to grasp the true scale of our universe. As we leave Earth's embrace, the first marker on our cosmic journey is the moon. About 384,400 kilometers away, a distance so vast that if you were to drive a car at a constant speed of 100 kilometers per hour, it would take you over 160 days to reach it. And from this lunar vantage point, Earth appears as a fragile sphere of blues and greens, cradled in the black void of space, a sight that puts our existence into a humbling perspective. This is Earth as seen from the moon. As we continue our outward journey, the next milestone is the Sun, lying approximately 1 astronomical unit away from Earth. This unit, equivalent to about 150 million kilometers, is the standard measuring stick for distances in our solar system. Imagine this: light, traveling at an astounding speed of 300,000 kilometers per second, takes about 8 minutes and 20 seconds to journey from the Sun to Earth. If you were to travel this distance in a commercial jet, flying at 900 kilometers per hour, it would take you about 19 years. This immense distance is a stark reminder of the vastness of space, even within our own solar system. The Sun, a fiery behemoth, provides life-sustaining energy to our planet from this incredible distance. Venturing beyond our home planet and its solar companion, the Sun, we set our sights on Mars, our enigmatic red neighbor. Mars, at its closest approach to Earth, is about 54.6 million kilometers away. However, this distance can stretch up to 401 million kilometers when the two planets are on opposite sides of the Sun. To put that in perspective, traveling to Mars at the speed of a commercial jet would take upwards of 50 years. This vast expanse of space between Earth and Mars has been a significant challenge for space exploration. The rovers and probes we've sent to the Red Planet embark on a journey that is not just far, but fraught with complexities due to the constantly changing distances and orbital dynamics. As we journey to the outermost reaches of our solar system, we encounter Neptune, the distant ice giant. Lying roughly 4.5 billion kilometers from Earth, Neptune marks the edge of our solar neighborhood. Sunlight, racing across the vacuum of space, takes about 4 hours and 15 minutes to reach Neptune from the Sun. This staggering distance showcases the enormity of our solar system. Launched in 1977, the Voyager 1 space probe represents humanity's insatiable curiosity and our desire to explore beyond known boundaries. As of now, Voyager 1 has traveled for over 4 decades, covering a staggering distance of more than 22 billion kilometers from Earth. It's the farthest human-made object from our planet, a silent wanderer in the cosmic sea. In 1990, at the suggestion of the renowned astronomer Carl Sagan, Voyager 1 turned its camera back towards Earth for one final photograph. This resulted in the iconic pale blue dot image. At a distance of about 6 billion kilometers from Earth, our planet appeared as a tiny, faint dot in the vastness of space. Sagan poetically reflected on this image, emphasizing our responsibility to cherish and preserve our only home, a small speck in the immense universe. At the very fringes of our solar system lies the Oort cloud, a vast theoretical sphere of icy objects. This distant cloud is thought to extend up to a staggering 100,000 astronomical units from the Sun. That's about 1.9 light years, a distance so immense that it's on the cusp of interstellar space. Scientists determine the boundary of interstellar space, known as the heliopause, where the Sun's solar wind is stopped by the interstellar medium. This is where the influence of our Sun ceases and the vast realm of interstellar space begins. The Oort cloud represents the final frontier of our solar system, a boundary zone where the Sun's influence wanes and the cosmic journey into the galaxy truly begins. As we venture beyond the confines of our solar system, our next point of interest is Alpha Centauri, the closest star system to our Sun. Located about 41.3 trillion kilometers away, this distance is equivalent to over 276,000 astronomical units. At such colossal distances, the AU, a measure so convenient within our solar system, begins to lose its practicality. Hence, astronomers use the light year, the distance light travels in 1 year, for interstellar measurements. Alpha Centauri is about 4.4 light years away from us. Considering our current space travel technology, a journey to Alpha Centauri is almost unfathomable. For instance, the Voyager spacecraft, traveling at about 17 kilometers per second, would take over 70,000 years to reach this neighboring star system. This immense distance underscores the vastness of space that separates the stars and highlights the challenges of interstellar travel. Our journey now takes us to the grand scale of our home galaxy, the Milky Way. Spanning about 100,000 light-years in diameter, this vast spiral galaxy is home to hundreds of billions of stars, each potentially hosting their own planetary systems. Within this immense structure, there's a tiny sphere known as the human radio bubble, extending about 100 light-years from Earth. This bubble represents the farthest extent of human influence in the cosmos, the reach of our radio and television broadcasts into space. Beyond this bubble, it's as if humanity never existed. Any civilizations residing in the vast majority of our galaxy would be oblivious to our presence, given that our signals haven't reached them yet. The scale of the Milky Way is so vast that our entire recorded history is but a whisper in the cosmic wind, undetectable beyond this small bubble. As we leave the Milky Way, we enter the vast, almost incomprehensible realm of intergalactic space. Here, galaxies float in the cosmic ocean, separated by mind-boggling distances. Our galaxy is part of a small cosmic neighborhood known as the Local Group, a cluster of more than 50 galaxies spread across approximately 10 million light-years. The Local Group is a diverse assembly, including not just spiral galaxies like the Milky Way and Andromeda, but also a multitude of smaller dwarf galaxies. The distances here are so vast that light from one end of the Local Group to the other would take 10 million years to traverse. This scale dwarfs anything within our own galaxy, underscoring the enormity of the universe. Intergalactic space is a silent expanse, a vast wilderness between the islands of galactic light. In this immense void, our galaxy, home to our entire history, is just a tiny speck among many, a single story in the grand cosmic library. As we extend our cosmic gaze beyond the Local Group, we encounter the colossal Virgo supercluster, an immense collection of galaxy groups and clusters, including our own Local Group. Encompassing a region of space about 110 million light-years in diameter, or 33 megaparsecs, the Virgo supercluster is a titanic structure in the universe, containing thousands of galaxies from at least 100 galaxy groups and clusters, each with their own myriad stars and planets. As we journey outward from the Virgo supercluster, we arrive at an even more staggering cosmic structure, the Laniakea supercluster. This immense congregation of galaxies, which includes the Virgo supercluster and extends over 500 million light-years, is our galactic home on a grand scale. Laniakea, meaning immense heaven in Hawaiian, truly lives up to its name. Containing the mass of 100 million billion suns, Laniakea is a gravitational masterpiece, with galaxy clusters, superclusters, and countless celestial bodies bound in a cosmic web of attraction and motion. At the heart of Laniakea lies the Great Attractor, a mysterious region of space that exerts a massive gravitational pull on the galaxies within this supercluster. In this vast expanse, our Milky Way, the entire Local Group, and even the Virgo supercluster are just tiny components of this gigantic structure. Laniakea provides a profound context for our existence. In this immense supercluster, we are part of something far greater and more majestic than we can fully comprehend. As we reach the boundaries of our cosmic exploration, we encounter the limits of the observable universe, an astronomical marvel stretching about 93 billion light-years in diameter. This begs a fascinating question. If the universe is only 13.8 billion years old, how can it be so vast? The answer lies in the nature of cosmic expansion. The universe has been expanding since the Big Bang, stretching space and increasing distances between celestial bodies. But what lies beyond the observable universe? This remains one of the greatest mysteries of cosmology. Some regions of space are expanding away from us faster than the speed of light, placing them forever out of our view. Consequently, the true size of the entire universe remains unknown and potentially infinite. The observable universe, vast as it is, might just be a tiny fragment of the entire cosmic expanse. We are left with the humbling realization that there might always be regions of space, entire galaxies and one.
Asking how big the universe is seems like a silly question. I mean, like, it's big, really big. How big, you might ask? Oh, I don't know. There's probably
Uh, Oh, excuse me, I've exceeded my range of my ability. Let's see if we can get back.
a your mama joke in there somewhere, but suffice it to say that it's ginormous. But ginormous isn't really a scientific term, although it should be. So seriously now, how big is the universe? Well, the first thing you need to realize is that many people misunderstand exactly what that question is asking. We first need to distinguish between the entire universe and the universe visible from Earth. Those are different things. So how much of the universe can we see from our vantage point here on Earth? Well, light has a finite speed, specifically about 300,000 kilometers per second, or about 186,000 miles per second, which means that when you see an astronomical object, you're seeing it like it was in the past. For instance, it takes light from the sun 8 minutes to get to the Earth. You probably knew that. But that has bigger implications. For instance, that means that there is a sphere around the Earth with a radius of the Earth-Sun distance where light takes 8 minutes to travel to us. And that sphere idea is true in general. There is a sphere around the Earth with a radius of a light year. If we could somehow send lots of super bright lights a light year away to surround the Earth and briefly blink them, what would happen is that the light pulse would take a year to get to the Earth, and they'd arrive at the same time. When we saw them, we'd be seeing a blink that was a year old from objects located a light year away. We can take this idea to the extreme and ask, what is the oldest thing in the universe? And that is, by definition, the moment the universe began. That happened 13.8 billion years ago. If the universe wasn't expanding, the farthest thing we would see would be a sphere centered on the Earth with a radius of 13.8 billion light years. This is what we call the visible universe. Inside that sphere, light has had time to get to us. Outside the sphere, it hasn't. We can't see anything outside that sphere. Now I should caution you and point out that the numbers quoted for the visible universe are true only if the universe isn't expanding. Of course, it is expanding, so the situation is a little more complicated. I made a video about how that changes things, and you might even want to take a look at it. But the bottom line is that there is a sphere centered on the Earth that is the extent of the visible universe. Is that how big the entire universe is? The answer to that question is almost certainly no. The universe is bigger than we can currently see right now. And you kind of already knew that. For instance, as we look out and see the light from the beginning of the universe today, we can see out to some distance. If we look again tomorrow, we will be able to see out to that distance plus an additional light day. That's because light traveling over the course of those 24 hours will be just getting here tomorrow. And inexorably, day after day, we'll be able to see a larger and larger sphere of the universe. There are locations that we cannot see today because the light simply hasn't had time to get to us that we'll be able to see tomorrow. Again, this ignores the complications due to the expansions of the universe. We'll get to that in a minute. So if the entire universe is larger than the portion we can see, how big is it? Well, to answer that question, we need to back up and be a bit more careful. Let's start with talking about the oldest and most distant thing we can see. As it happens, we can't see the moment the universe began. That's because the early universe was so hot that light couldn't pass through it. You can sort of think of it like a fog. However, there was a moment about 380,000 years after the Big Bang when the universe cooled enough to become clear. The temperature at which that happened is about 3,000 degrees centigrade, or about 5,400 degrees Fahrenheit. Everywhere in the universe, the temperature was identical, and at 3,000 degrees, it was glowing hot. So you'd think that when we looked out with our telescopes, we'd see a glow about like what looks like when you see inside a steel mill. But this is where the expansion of space comes in. Since that moment, the universe has been expanding and cooling and even stretching space. The upshot of that is that what once would have been viewed by the human eye as white is now no longer visible and can be only seen by radio antenna capable of detecting microwaves. For that reason, this oldest thing that we can actually see is called the cosmic microwave background, or CMB, and the temperature of the universe in the current day is now 2.7 Kelvin, or minus 270 degrees centigrade, or minus 450 degrees Fahrenheit. Pick your favorite units. So that's the first big thing. This microwave radiation that measures that the current temperature of the universe as 2.7 Kelvin is a fossil remnant of light emitted when the universe was about 3,000 degrees. This temperature is almost the same everywhere, but we've learned that there are very small variations in the universe's temperature. These variations really are incredibly tiny. The hottest and coldest spots are only 0.01% different from the average. Our current best measurements of these variations comes from a telescope in space called Planck. Astronomers using the Planck Observatory have measured the entire sky, and their map of these temperature variations is what we see here. The blue spots are colder than average and the red spots are hotter. So those temperature differences are pretty and all, but what do they have to do with the size of the universe? It turns out that these variations were caused by sound waves in the hot universe just before it became transparent. And because we know the temperature the universe was at the time, and we've measured the total amount of matter we can see in the universe, we can calculate the wavelength of those sound waves. It's a complicated calculation, but it's a straightforward one. And I want to emphasize that there is no guesswork on this. We have heated matter to these temperatures, and we've measured the matter we see in the visible universe. We know a great deal about the wavelength of sounds that were present. Sound in the early universe is pretty much the same as sound you used to hear me. Sound is transmitted through variations in the density of air, and you can hear a variety of frequencies. In the early universe, the regions of higher and lower density, due to the sound waves, result in hotter and colder spots in the cosmic microwave background. And given that we know the wavelength of the loudest sound in the universe before it became transparent, we can calculate the angular size of the most common sizes of hot and cold spots in the microwave background. Further, we can calculate what size is most likely, and it should be 1 degree as viewed from Earth. Okay, so now we're getting somewhere. We have a firm prediction of the size of the hot and cold spots. This brings us closer to our question, which I remind you is the size of the universe. Now that prediction of 1 degree depends on the shape of the universe. Remember that Einstein's theory of relativity says that space and time can bend and morph. Space could be one of a variety of different shapes. It's hard to imagine this in the 3 dimensions that we know space really is, so we have to substitute a 2-dimensional analogy. Bear with me. A flat 2-dimensional space is like the surface of a table. Flat means flat. But a two-dimensional space could be like the surface of a globe, where, if you kept on walking, you could, in principle, end up back where you started. This is called a closed space. Another possibility is space could be shaped like a saddle. This is an example of what is called an open space. So those are the three basic possibilities of the shape of space. How does that fit into our question? It comes down to the fact that light travels in a straight line in space. But if space is curved, then we can get fooled. Let's use the hot and cold spots in the microwave background to see what I mean. If space is flat and a distant spot in the microwave background is 1 degree wide, then we will measure the size as 1 degree. This is the simple mathematics of triangles that you learned in geometry class, where straight lines travel in, well, straight lines. But that behavior doesn't have to apply. Let's see why. For instance, if two ants were in flat space and they were separated by a certain distance and started walking parallel to one another in a straight line in that flat space, they will always stay the same distance apart. If you do the same thing on a closed or spherical space, the two ants will eventually run into one another because straight lines in curved space are curved. This is like lines of longitude on a globe, where they are parallel at the equator, but intersect at the pole. And the opposite is true in an open space like the saddle space. There, the two ants, initially a fixed distance apart from one another and walking in straight lines, will eventually diverge and get farther apart. That's just curved space for you. So this has consequences when measuring the apparent size of these distant spots in the microwave background. If space is flat, the line that crosses the spot you're looking at and the two lines that go from the edges of the spot to your telescope form a common triangle. But in an open or closed curved space, the triangles are distorted. Let me be more specific, because this is super important. In a closed or spherical space, what one would expect to be a straight line is curved in a specific way. The crucial effect is that the angle of the triangle near your eye is bigger than if space wasn't curved. The opposite is true for an open or hyperbolic space. Here, the curvature is in the opposite direction. We see that the angle of the triangle near your eye is smaller than if space isn't curved. Now, the telescope can't see the whole path traveled by the light. All it sees is the angle of the light coming into your eye or the telescope, with a closed or spherical space being bigger than expected, and the angle seen in the open or saddle-shaped space being smaller. And if we apply this to the spots in the microwave background, this means that a spot that is 1 degree wide in flat space will be different in a curved space. So this is a perfect way to test whether space is flat or curved. In a flat space, the dominant size of the spots should be 1 degree. If space is curved and closed, the spots should look bigger. If space is curved and open, the spots should look smaller. So what did Planck and other experiments find? A drum roll, please, maestro. The measurements found that the size of the spots is 1 degree. From that, we conclude that space is flat. Or can we? Well, yeah, sort of. But that's an incautious statement. Physics is an experimental science. When we say that the Earth is flat, what we mean is that the measurement is consistent with being flat. But that also means that the measurement is consistent with a tiny bit of curvature. For example, if we're at the beach on the ocean and look at the horizon, it surely looks flat. But in spite of the claims of some people, the Earth is most certainly not flat. It's a sphere. So you have to keep this in mind. What appears to be flat can indeed be curved. And when we measure the Earth, we can only say that it appears to be flat. And that's true of space as well. Space appears to be flat. If, and I repeat, if space is flat, then the universe is infinite in extent. Our visible universe is just a small bubble in an infinite sea. Similarly, if space is shaped like a saddle, what scientists call a hyperbolic or open space, space is also infinite. But what if space is closed and shaped like a sphere, but so big that it looks flat, like the Earth can look flat? Well, in that case, space is not infinite, it has a finite size. So now we're getting somewhere. If the universe is closed, how big is it? Well, if you do a careful analysis using the maximum possible curvature allowed by the best measurements, you find that the universe can be no smaller than 250 times bigger than the visible universe. So that's your answer. I mean, we've always kind of thought that the universe is big, but now we can hang a number on that. The visible universe, meaning the part of the universe that we can see using our instruments, is a sphere centered on the Earth and, taking into account the effects of expansion, with a diameter of 92 billion light years. However, the entire universe, including the parts that we can't see, is at least 250 times wider than that. And the universe could indeed be infinite in size. We've come a long way from simple speculation about the universe. Seemingly intractable questions are now getting answers, and that is your fascinating fact for the day.
Okay. Well, you're going to have to pardon the technology glitches there, because believe me, I know nothing about how this stuff is supposed to get from here to here. I still find that fascinating, and I probably watched that video and videos like that many, many times. And I wanted to say a couple of things, though. First place, the man you heard talking is Dr. Don Lincoln. He's a theoretical physicist at the Fermi Lab, which is part of the University of Chicago. And he has made a number of videos that deal with this subject, and there are a lot of them, and there are a lot of different things you can look at. But he might have misled you a little bit. First place, there was no air at the beginning of the universe, so the sound was not propagated through air. Sound has to have a medium, and the medium here is the air between you and me that lets our voice go. In the early days of the universe, when he heard him say it was very, very hot, there wasn't any air, but there was what was called a baronic medium, which was the quarks and other subatomic particles that were bouncing around so fast because the temperature was so high that it couldn't coalesce into atoms like lithium and hydrogen, and helium. But it would transmit sound. So the sounds were transmitted through that baronic medium rather than through air. The second thing that I wanted to talk about, because it is so, so important, is how do we know the universe is expanding? In fact, Dr. Lincoln did another video on that, which I didn't have time to bring in and show, but I'll summarize it. You've all heard of the Doppler effect. The ambulance is roaring down the road and you hear it, and the pitch gets higher as it approaches to you, and then when it passes, it gets lower. Well, that same thing is true in any of the electromagnetic medium, any of the spectrum. And when light is coming towards you at a very fast speed, it shifts toward the low end of the spectrum, or the short, which is blue. If it's going away from you, it shifts toward the red end of toward the high end of the spectrum, which is red. So by measuring the amount of that redshift, and this has been done precisely in laboratories here meaning all over the world, very precisely, they know that the degree of redshift corresponds directly with the distance that light source is from you. And the light source that they're measuring is a galaxy. And they have instruments that are so fine, they can pick at a single galaxy 20 million light years away and do a spectrograph on the light coming from it and find out what the redshift is. So that's extremely important to know that we have a way of making these measurements. It's also important to know that the instruments that were in the sky, you heard him say the Planck, there are several others that are up there that have specific purposes in the sky. And the most famous one is the Hubble Space Telescope, which launched, I believe, in, I've got it down here, probably about the 1990s. And as a matter of fact, when the Hubble first went up, there was a flaw in the lens. They thought the whole thing was wasted. It's like being nearsighted. So they had to spend millions of dollars, send a crew up and do a corrective procedure on the Hubble telescope to essentially put bifocals on it. So at that particular point where it was not focusing correctly, it was correct. And then everything was fine. And it's made some spectacular pictures. And I'm sure over the years you've seen a lot of them. However, Hubble's range is limited for a couple of reasons. One, the size of its lens and the fact that it is primarily optical and does not measure in the spectrum that is outside of visible light. And you know, our eyes see light, and in the total spectrum of electromagnetic radiation, light is a tiny, tiny sliver. It goes a long way this way and a long way that way, but we're focused on the light. Well, a few years ago, another space telescope called the James Webb Space Telescope was launched. And it is primarily designed to see the sky in the infrared, through infrared and its mid-infrared cameras. So it's looking not at visible light, but at light that's outside our field of view. And the nice thing about that is, as I told you, as things go farther away from you, the shift is toward the red. And in fact, long enough, given enough time, white light, the light that you see, which is everything, that shifted toward the red has shifted all the way out. And now you're down to gamma rays and cosmic background. And you saw the picture of the cosmic background on the screen. That's obviously, and that happened a long time ago. However, now, as these objects are racing away from us at fantastic speeds, the degree of the redshift lets us know exactly how far away they are. And actually, it's I find that just mind-boggling that can be done. The next thing, you heard Professor Lincoln say that, okay, we've taken these measurements and we've concluded that the universe is flat. Now, by that he said almost flat. It's in other information, there's a 98.75% certainty that the universe is flat, which leaves there's a 0.25% possibility that it's not. You also have heard him say that if it's not flat, then the size of the, if it's not infinite, the size of the universe must be at least 250 times its present size, which is 93, 92 billion miles. Well, you multiply those numbers and you get a universe, if it's not infinite, is at least, let me see my number here. Well, I've written it down. 250 times larger, which is at least 24 trillion miles in diameter.
Not miles, light years.
Light years. I beg your pardon. Somebody corrected me. Right, light years in diameter. Huge. You know, you might as well forget about it. You can't even conceive of what that is. And you think about us here. You know, trying to run 100 yards gets me out of breath. Well, light going at that speed goes all the way to the end of the universe in a number of many light years. So you know it's got to be traveling fast. The other thing, 250 times larger than the observable universe, high probability that it is actually flat. And if it's flat, then although we don't know, the likelihood is that it is infinite. Now, if the universe is infinite, who knows how many stars there are? There could be a finite number of stars in an infinite universe, but the likelihood is that it's not. And also, whether it's infinite or just terribly large, there are between, let's say if it's finite, not infinite, then the best estimate is that there are at least 100 billion, perhaps as many as 200 billion galaxies in the known universe. And each of those galaxies has approximately 100 billion stars. So that puts the star count in a finite universe between 10 sextillion and 1 septillion. Again, staggering numbers. Or those who are mathematically inclined, that's 1 times 10 to the 22nd power, or 1 times 10 to the 24th power. And if it's infinite, nobody knows, and there's no way we can know. All right, a couple of things we need to talk about, or at least I'd like to talk about. With all these septillion billions of stars out there, is there life on any of it? I can practically guarantee you that unless there's life in our solar system that we haven't yet learned, or possibly in the nearest star system, which you heard they say Alpha Centauri, which is 4.2 light years away, we'll never know. And even though we're sitting here listening for radio waves coming from in the SETI program, which you've probably heard of, Search for Extraterrestrial Life, we'll never know. It's just staggering to me to think of the fact that there could be millions of civilizations somewhere, but we'll never encounter them. And now I'm not talking the Captain Marvel stuff and the science fiction of warp speed and wormholes and that sort of thing. I'm talking about the known science today. It's just there's no way that we'll be able to come to them, or that they'll be able to come to us. And I shouldn't say no way, because who knows what some technology may be invented sometime in the future, but it doesn't look like it. Another thing you need to think about, an infinite universe implies no beginning and no end. Well, we've already said that the universe began 13.8 billion years ago with the Big Bang. The way some cosmologists get around that is they say the Big Bang just created our small part of the universe, that we are a part of a larger universe, which again, if it's infinite, you can see how, although it's hard to envision, you can see how a particular phenomenon could have occurred in only a small by the size of the universe, part of an infinite larger universe. That's all theory though, and no one can prove that. And no one, I don't know, they talk about tests they're running to see whether there are parallel universes or whether there's something else out there that doesn't interact with our universe. But if you do any researching on your own, I urge you to go to good, solid sources like Fermilab or University of MIT or Caltech or NASA, the European Space Agency. There's a lot of good stuff. There's also a lot of garbage and a lot of misleading. And they'll tell you that there's a new change a new discovery that's going to change everything. Well, if you read that in the headline, avoid that article. Just don't waste your time on it. Now, one other thing. Where does God fit into this? As Albert Anderson told me a long time ago, Laplace is supposed to have said to Napoleon when asked about God and his equations, Laplace said, my equations have no need for that hypothesis, the God hypothesis. And Nobel laureate Steven Weinberg, who's deceased a couple of years ago, told us in his studies that the more he understood the universe, the more pointless it seemed. He doesn't know why it's here or what it's for. And then you've got Genesis that said, in the beginning, God created the heaven and the earth. And that is certainly a implication, if not outright stated, of an eternal and an infinite heaven. And so we may have gotten around to being where the writers of the Bible were millennia ago. We've got an infinite universe now. The American Association for the Advancement of Science, to which I belong, reports that half of their members believe that there is what they call a universal force, that there must be some sort of intelligent force in the universe, call it prime mover or God or whatever, because there's so much that science cannot explain, such as how did life begin, or how did the universe begin? And others say that, well, give us enough time, money, and equipment, and we'll figure it out. I'm not sure which side of that argument I fall on, but people always want money and equipment. And one final thing, and I'm a big fan of the space program, but it is very, very expensive. And there are a lot of politicians that say, why spend the money on it? Why spend $10 billion to create the James Webb Telescope? Why spend $100 million a year to operate the Hubble? Why spend all this money on theoretical physicists and cosmologists sitting in ivory towers thinking about this stuff all the time? I don't know. I can't answer that question, because the answer that comes up, it's going to be very expensive. And you may not get any further than where you are already. Thank you for having me. I hope you enjoyed it. I'm sorry I didn't get all my technology worked out, but I hope you'll pursue it on your own.
I don't think anybody has any questions, do you? Anybody, if you have questions, use the microphone. Okay, Tony? Can you use the microphone so these folks can hear you? Thanks. Green light, got a green light?
So on the subject of intelligent life somewhere else in the universe, not just life form, I think it's a statistical certainty that there's life form in planets that are not too close to their stars to be fried and not too far away from their stars to be frozen. That's statistically certainty in my opinion. So I'm asking not about life forms, but intelligence. And what are your thoughts about these UFOs unidentified flying objects now have a different name now, most of which are seen over the oceans. They're traveling at unimaginable speeds that have been tracked by our fighter pilots with computers and making right angle bends in their trajectory. And no life form on our planet could withstand that. So that suggests that maybe they're driven by some robotic mechanism with artificial intelligence, who knows? But what are your thoughts about these observations that the military has made for decades, and now that the government is coming out with more and more?
Well, in a very short period of time left, the majority of science debunks all of that. It's not, it's either the observations are incorrect, or the facts are overblown, and it's not given credit. Now, I'm not saying, as I said, I don't know, but the majority of the scientific community puts no stock in any of that. And you can feel differently, you can think otherwise, but that's where it stands.
So they put no stock in the observations about the trajectory or the speed of these objects.
Some other explanation. And I'm sorry we've run out of time, because this is a fascinating subject and you could talk about it, for a long time. But
You could.
do some research on it. There's lots of material out there.
All right. Thank you, sir.
Does anybody who's watching us on Zoom have a question? George?
The reason why we explore space or inner space or anything else is because our language allows us to ask why and how.
I agree with that 100%. And I would tell the politicians, stop spending it on war and spend more of it on space.
Any other questions? We're just about out of time. All right. Thank you, Tim. That was great.
Thank you.
And despite what Tim said, he's also a scholar and a lawyer.